Hey, y'all. Oh, this I got to tape. Oh, we are taping. Okay, good. We'll start here in a couple minutes. Got to whoop down some breakfast real fast. We got toasters in, toaster ovens, and I found some old waffles. Hadn't used in a while. Normally we have, in the morning we got coffee going, orange juice, and muffins, and sometimes somebody brings an egg casserole. We got pancakes. Normal. Pretty slim pickings these days. These frozen waffles are probably a year old. That's all I got. All right. All right, so I guess we get started, huh? Go ahead and share the screen. We tried to watch the launch this morning. The SpaceX had a launch. I'm going to erase all this stuff. SpaceX had a launch. Take a picture of that real quick. They were launching 60 of their satellites into orbit. And so we watched the countdown. And then, unfortunately, they had to, the last 40 seconds, they canceled because of weather. So that was a bit of a letdown first hour, but if we can catch a live something, we'll try and watch a live something. It's always fun to watch those because, you know, I'm trying to erase what happened last hour. Okay, let's just do that. Let's do that. So I'll give you a preview of, okay, erase that. This is the one that I'm recording. So I want this to look nice. Okay. The hardest time is always between first hour and third hour because there's no time. I had to get my coffee and go to the bathroom, get my waffles. Okay, let me shut that down. All right, so here we go. I did a bunch last hour, geez. Okay. So here we go on to today's topics. Yeah. Let's share the screen real quick. I even have props. All right, so move you guys up here. And feel free to start using on those comments. Some students are shy, and you can do private comments. And if you say anything, okay, so Emerson's having submission issues. If you say anything, you know that usually what you say is fine. Let's start off with Emerson here. He says I'm having submission issues on Canvas. I keep submitting things, and then when I check it later, it keeps saying I haven't submitted it. Well, if you try and submit 1.1, 1.3, 1.5, it's not going to take them because those are not to be submitted through Canvas. Those are submitted through paper, which will turn in the paper copy on October 15th. Now, course quizzes should be no problem. You just got to take them. You don't need to submit. I mean, you hit the submit button, but there's no picture to take. The only picture we've taken so far is of 1.2, 1.4, now the take-home test. And sometimes you have to submit them in one of those 4 formats. Hopefully, Canvas would tell you if you're submitting it into a format that won't work. So the take-home test, if you're make sure that if you take a picture with your iPhone, it puts it into this, you know the way iPhone, which I hate, it does this little thing where it has a little movie, like there's movement, like they think that's so cool. It's irritating. So it won't accept that. You have to convert it as a JPEG, because that's the Canvas won't take the HIVAC, whatever it's called. Okay, so do that. Change it. There's a way on iPhone to change it to submit as JPEG. Like turn off that stupid movie thing, and that's what people have trouble with. Yeah. So I mean, I can sometimes. I used to be able to take that, but then it took me a couple of minutes. I had to go through and redo it, which is a pain in the butt. So I said, no, I'm not gonna. Yeah. So give it a try. Change it to JPEG, PDF. You can save it as a PDF and then submit it. That'll work. Yeah, you can save as PDF and then submit. It shouldn't be a problem. I don't know it from the students' end very well. Okay, so people are still having some troubles on submitting stuff. But for the most part, of those tests, I think this morning I saw that I had 60 have been submitted out of 81. Get that take-home test in, submit it today. You'll just lose 10% today, but it's 20% tomorrow, 30% the next day. I'll tell you what, I'll only take off 5% today, okay? This is a special. Since it's the first time, I'll just take off 5% today if you turn it in. So that's only losing about 3 points for being late. Now, I'm posting the key on Wednesday. So tomorrow, you make up for it. It's 15% off tomorrow. All right, just made that up. Okay, so here we are, sharing the screen. We got a lot to cover today. Announcements for that take-home test. We've done now 2 help sessions. We did one Wednesday morning last week during office hours, and we did one last night from 8 o'clock to 9 o'clock p.m. I recorded both of those. They're on YouTube. It's under public, but they're on my YouTube channel. Sometimes if you want to get to something quicker than you normally would, if you'll subscribe to the YouTube channel, Askey Physics, you'll see videos before anybody else does, and you'll get heads up that there's a new video posted. It takes me a while to get it back on the Canvas, or on Facebook. You know, it takes a little while, but it'll be posted on YouTube first. So that's a good idea to go ahead and subscribe. All right. I also give good makeup tips on the YouTube channel. How to use the blush. Okay, let's keep going. You're a tough audience, man. Monday morning. All right, so remember on these weeks where we're all virtual, there's no night Zooms. No night Zooms. So speaking of schedule, this week we're virtual. Next week it's alternate, but it's a different alternate schedule. Monday is group 1. Tuesday is group 2. Wednesday is virtual. All right. Hey, good job, Emerson. Went through. So good news. Okay. Now, so this is a coming, but first hour in their wily ways talked me into pushing this back to October 15th. It was October 13th. It was originally October 8th, but then I found out that was fall break. So it got moved to October 13th. But that's like the day after we come back, and we're all kind of as one unit, except for the virtual kids. So that ought to be rather crazy. So I thought, wait, I'm not going to throw a test in there. So we're pushing it back to the 15th, which is a Thursday, October 15th. And normally this test is already given about October 1st, so it puts about 2 weeks behind. But we'll be working, we'll be into packet 2 by then, hopefully. but that's okay. The test will cover packet 1. It'll cover what's on take-home test 1A and 1B. Speaking of take-home test 1B, that's also 75 points. You'll get that Thursday evening, probably, maybe even Friday, as late as Friday. It depends on how much we get done today and Thursday. Probably maybe Friday I'll drop that thing because, and then give you a week to do it, okay? At least a week. You always get at least a week to do a take-home. All right, keep going. And but the big test though is not till October 15th. So last time we did the 2D motion, and this is on screenshots, and there's a help video of me going through all this back last week, or go to YouTube. There's the, woo, look at that. There was the key. So that was the key to 1 through 6, which if you're quick on the fingers, you can, I am recording. Oh man, I'm recording this, you idiot. Well, I guess if you go back and watch the recording, I don't care. I mean, you go back, I want you to turn something in right. I don't want to just copy off the key, but if you were fast enough to catch that, or you catch the recording later on today, oh, I take it back. Recording's not posted until tomorrow at noon, but this is not due. This is not due until Wednesday. So it got pushed back to Wednesday this week at midnight. I'm talking about sheet 1.6. So for this week, the take-home test was due last night. 1.6 is due Wednesday, and that's it. Okay. 1.7 we're going to turn in with the sheet. So it may be the 1.7, 1.8, it's all just turned in by sheets when you turn the packet in. So that may be the last submit, except for take-home test 1B for packet 1. I think so. Okay, because various reasons. Well, last week we started talking about black kinematics. So we're going to talk about that more today. And today we're going to work problem. We're going to wrap up this. We're going to work problem 10. We're going to work problem 11, and this will probably end up being homework. One problem. I know. Yeah, so 1.6, you have to finish the front and do number 12. But let's get this other stuff done. We'll also develop a new equation today that we can use. Okay, so we'll get to this here in a minute. Let's go back and review what we've talked about. We talked about theta, we talked about all this stuff. We talked about the puppy. So we looked at this little puppy, and we measured it with a timer, and we saw that it went in 5 revolutions. It took the puppy 10 seconds to go around 5 revolutions. So when you do, it's 2 pi radians per revolution, as we said, and so this puppy is going at pi radians per second. So when you think pi radians per second, we can convert this later on. We can remember this. Remember the puppy. This is what pi radians per second looks like. If that puppy was going at, in other words, that's 1 revolution in every 2 seconds. It goes around once every 2 seconds. If it was going 2 pi radians per second, that'd be twice as fast. That'd be like a dog chasing its tail or something. Okay. All right. And last time we showed you the Frisbee, and we showed this. So we did that, showed where pi comes from. It's a relationship between the circumference and the diameter. We looked at this. This is, we talked about LPs. I brought out my Beatles or something, whatever album I had that day. Led Zeppelin or whatever it was. And this is a long play album. We said, well, that fly is going around and around, and the fly is going at some speed, which is 33 1/3. RPM stands for revolutions per minute, which is how, it's a good way of talking about it, RPMs. Like your car, your tachometer on your car measures the RPMs of your drivetrain. So like normal cars are going around 2,000 RPMs. If you're tooling down the highway at 60 miles an hour, you're at about 2,000 RPMs. If you're trying to get up a hill, it may bump down to lower gear and go up to 4,000 RPMs. When it gets to 6,000 RPMs, you're redlining. That's kind of dangerous with your engine for a very long time. And then we said, well, we have two different worlds here. We have linear world, which that's red equations. So we did V is equal to R omega. And then we have, oh, Emerson, your mic's still on. So there you go. I didn't want you to start cussing me out, and then it's awkward. Now everybody can cuss me out all you want now. That's what I do to our principal anyway. But I always check when I cuss out my principal. I always check to make sure. This is the tip. I always make sure my microphone's turned off. That's a pro tip for you. All right. So then we said there's circular world, and circular world is analogous to linear world. And that is omega, instead of V is equal to delta X over T, which is basically the red equation we have hanging from the room, will now hang from the ceiling, which you don't see right now, but black equations, which is omega equals delta theta over T. So delta theta is like delta X, T is T, and then V is like omega. Those are the analogies. So that fly on this LP, yes, the fly is moving around and around at so many inches per second, but it's also moving around at 33 1/3 revolutions per minute. Normally we don't use revolutions per minute, we use something called radians per second. And let's go back, this is all kind of review, but let's go back and here we go. So what is a radian, again, from last week? We said, well, and I showed you an animation on this, but we said a radian is this, these are radians, this delta theta, that's radians. You would say degrees, and we will say degrees too. We use degrees in here. I mean, I'm not saying we're never going to use degrees, but radians are superior to degrees when it comes to physics or any kind of upper level math, because they have the benefit of not having any units. And the reason why is this delta theta, it's simply a ratio of delta S over R. Now somebody, why don't somebody look up historically, Wikipedia here, and you can post this on Facebook I'll give you 5 Facebook points. And these are points, they're points you get to use if you need them. Like if you're down to a 89.1 at the end of the semester, and you go, oh man, I need some points. And you go, oh yeah, Facebook points. So you go collect all those, take screenshots, show me, look, here's where you give me Facebook points. And then you get the A. Okay, so these are used in case you need them. Anyway, so I get 5 Facebook points for somebody to come back and look up, just Wikipedia, whatever, the history of radians and when they were first used. I know degrees is, that's the Mesopotamians. Those are really old, Babylonians, I mean, way back. But when do they start using theta as a measure of circular motion? I should know this, but I don't think I remember this. Anywho, so that would be kind of cool. So delta theta is, blow this up here. Delta theta then is basically a measure of the arc length of, if I'm doing this Frisbee, it's the arc length versus the radius. Arc length versus radius. So if my arc length's way over to here and my radius is there, that would be, well, that would end up being 2 pi, sorry, pi to here, all the way around is 2 pi. That is pi over 4, right? Pi over 2 is 90 degrees. Pi over 4 from here, this being my starting point. Pi over 4 is 45. Pi over 2, okay. Pi over 3 would be 60. All right, et cetera, et cetera, et cetera. All right, so it's just a way, once we end up on that hotel in space, and you all will, my prediction is you will spend maybe your honeymoon, not your honeymoon, maybe, let's say your 20th anniversary with your special person, you'll spend that on the space hotel. let's say the 25th anniversary, you'll treat each other. And on that space hotel, you're going to know pi pretty well, because that's how they're going to talk about distances. They'll say, well, the movie theater is pi over 3 radians away from you. It'll be easier to talk that way. Okay. Enough of that. So they don't have units because it's arc length, which is meters, over radius, which is meters. So meters over meters, the green kill pin kills both of those, and we end up with no units, which it freaks out students, but there's no units. Still kind of review. Okay, now something new. Okay, this is new material. So if you've been half asleep, wake up. Sit up in bed. Drink some coffee. Slap yourself in the face. Pour some cold water on you. Here we go. So new stuff here. This is the omega vector. And we said that omega, remember we said omega is the change in position and change in angle over time. It's analogous to velocity, but it's linear world velocity. Radians per second. Okay, like the little puppy was going pi radians per second. That's their omega. So omega is a vector. See the little you see the little vector symbol, little arrow above it means it's a vector. And we're lazy. We don't always do that, but and the R is a vector. So notice that this is a three-dimensional thing, and the R, that whatever this thing is, that's going to rotate. This could be the puppy. It's rotating around and around and around. Looks like a counterclockwise direction, right? If I'm looking down on it, it's counterclockwise, which is the opposite way the second hand moves, counterclockwise direction. So CC, we say it's CCW. It's moving in a counterclockwise direction. And so the question is, how would you, if omega is a vector, vectors have to be straight. They have to be arrows, but we don't have curved arrows. Michael Faraday in the 1850s tried to introduce the idea of curved arrows, and he got laughed out of the auditorium. Okay, so yeah, well, tea is good too. Tea makes me really hungry. I don't know why. I could drink coffee all day, not get hungry at all. But if I drink one cup of tea, I'm starving like an hour later. All right, so how do we, so you can't, in other words, it's tempting to say my omega looks like this. My omega is this curve, right? But that's a big no. No, you can't do that, okay? These vectors have to be straight arrows. So let's get rid of that. I don't want you to think that's true. So here's something called a right-hand rule. So everybody take your right hand, okay? Not left, not your left hand, your right hand, okay? I'm assuming you're holding it up. Take your right hand, and then you take your fingers and you curl those in the direction, say curl your fingers clockwise, counterclockwise. Curl your fingers counterclockwise. All right, notice that when you curl your fingers in the counterclockwise direction, your thumb is pointing up, okay? It's called the right-hand rule. There is some left-hand rule stuff, but that's not till you get to be a junior in college. Right-hand rule. And you can Wikipedia, you could Google what right-hand rule, and then the images, and you'll see a bunch of these little things. The right-hand rule is used all the time in physics and electromagnetics. It's used a lot in electromagnetics because magnetism goes in one dimension, the electric field goes in the other dimension at 90 degrees, and so light waves, when they propagate through air, propagate like this. They go in, they curl. Light waves do that. That's why you can polarize glasses. Anyway, I'm getting off the subject. But that's the idea, because things are always curving, right? All right, so my right-hand rule. Now, if my thumb then represents the omega vector. The omega vector is in the Z In this case, if this is XY, see if I can draw in 3 dimensions here. I'm trying to make this nicer because I'm going to put this on the, if I blow it, I'll just wait till tomorrow. But X, say that's Y, and just lost it. Daggone it. Let's say this is X. Okay, that's Y, that's X. So you're seeing 3 dimensions here. This then would be Z, right? That'd be the Z axis. So when this circular motion is clockwise, my thumb points in the direction of the omega vector, up. Now make it go counterclockwise. So Olivia, Natalie, and Harry, I can't see you guys, so I'm assuming you're doing it. But now do your fingers, curl them the other way, count in the clockwise direction. When I do that, notice my thumb is pointing down. And that is negative. That would be negative omega. So you can have positive. So positive omega equals counterclockwise. Negative omega equals clockwise. CW. Okay? Let's just get that. I know it doesn't seem like it makes any sense. Let's get that out there. So when you're watching physics, when you go by the physics room at OU and it's engineering physics and you watch those kids take a test, you'll see these physics kids doing all this kind of gang sign stuff with their right hand, trying to figure out whether the thing is going clockwise or counter, which way the omega vector is. Now it's not just omega. I mean, there's something called angular momentum. There's all these other things, torque, for instance, all these other things that are in the 3rd dimension that you have to use right-hand rule to solve. You can do this kind of thing too. So you'll see some doing this, and this really seems like gang sign. You don't want to do it out in the street. Watch where you're thinking about a physics problem. You might just get shot. All right, let's keep going. So now you all, I'll do a demo here. Let me spin this basketball on my finger. No, I can't do that. So let's talk about a spinning basketball. Let's say that the basketball is spinning this way. Okay, watch the red little ball. So now watch the red pin. So the basketball is spinning this way. Now you draw on there. Where would the omega be? Draw me omega. Write an omega on there. Where do you think it would be if this is say the little puppy running around in circles? Where would the omega be? How would you show omega? And notice that I am going counterclockwise. How do I show omega? Anybody want to describe it? Logan's correct. He says put it in the middle. I'll go with that. I'll give him a point for that. He goes in the middle, and what does it look like? Circle and a dot. Brendan nailed it. So Logan gets a point. Brendan gets a point. So I put a circle because it is coming out of the page at you. So I put a circle with a dot in the middle, and then you want to write in there positive omega. And then you would have a number. Like, I don't know how fast I was going. Let's see. Let me count that up. That looks like, it's about like the puppy. So that is probably pi radians per second. That okay, let's go to here. Let's try another one. Now let's do this one. And okay, watch this one now. I'm gonna go faster then. Okay, now you on your paper do this and tell me how would you show that? How would you show this one? Look how fast that one's going. Let's see. Okay, that's probably enough. But it's fun. Okay, so that is what would I do? How would I show that? Just a dot, but the problem is I'm going clockwise. So clockwise is this. How do I show a vector going into the page? I don't know if we talked about it.
Omega.
Yeah, there you go. X, X, X. Somebody jumped in there too. Is that Brittany? What'd you say, Brittany?
I was thinking a negative omega, right?
It is a negative omega, but the symbol-wise would be an X with a circle around it. That is negative omega. So I got to give Brendan another point there. So that is, and I'll give you a point there because it's negative omega. Okay, good. And I was going fast. So let's say I was going at 3 pi radians per second. So I'll blow it up so you can see it. So that's how you would show that. Okay, X shows your thumb into the page. You go, well, that's well and good, Mr. Askey, but it doesn't affect my life. But it does. Circular motion's all over the place in your life. Oh, okay, now let's also talk about this. So I said it was 3 pi radians per second, right? But that's not how you see it. You see this as 3 pi inverse seconds. This is the proper way to say it. What? Inverse seconds? What? Well, let's look at radians for a second. What the heck is a radian? Well, we said that if I have a radian, that would be a delta theta, which is radians. That's S over R, and S is in terms of meters, and R is in terms of meters. So radians have no units. So the deal is no units. And so the proper way of saying it is just inverse seconds. You just ignore the radians. Radians is a word. It's not a unit. That's one of the things students can't get in their head. Radians is not a unit. You might as well call them Fred, okay? Because it's just a name. Freds per second. Okay. So let's keep going. Now, oh, okay, hold. Here's a question. So let's play with this idea. And here's your first question for the day. And the question is, what is the omega, which is this baby's bottom, of the Earth rotating on its axis? All right, so in other words, you're an alien, a flying saucer, and you're studying the Earth, and so you come down upon, oh, here's the Earth, I got the Earth. I got props. So we have an Earth here, and I come down, the Earth is spinning. Now the Earth spins, first off, is the Earth spinning clockwise or counterclockwise? From the North Pole. If I stand up here, if I look, that blows back. Okay, if I look down on the North Pole, does the Earth go clockwise or counterclockwise? Think about sunrise, sunset. Here's United States, here's Oklahoma. Here we come around and around and around, right? I mean, sun rises, okay, you know, Jacob's saying counterclockwise, let's see. Sun rises in the east, so we kind of come into, the sun stays over here, and we kind of come into it, so that makes sense. So I'm gonna agree with Jacob that the Earth is rotating counterclockwise, okay? So you're looking down, and my question is, what is the omega of the Earth? Now, here's a cool way of doing this, maybe, so that more people can get points. If you will privately answer me, then I can give it to 2 or 3 people. If we do it public, then once one person answers it right, then the game's over. So now, privately answer, what would be the omega of the Earth in terms of Okay. Criminy. In terms of inverse seconds, I should always tell me the units I want to get. I want you to give it to me. In terms of inverse seconds, that means 1/seconds. That means radians per second. Okay, that's the unit way of saying radians per second. So how many radians per second is the Earth rotating at? From looking at it from down from the North Pole. And privately answer for 2 zoom points. 2 zoom points. I give first 3 people, I'll give you 2 zoom points each. Nobody yet. So let me do a little better drawing here. Here's the Earth. Our eyeball is up here. We're looking down. We're looking down on the North Pole. And Jacob, we've already established then that it's going counterclockwise from our point of view. And we have some answers starting to come in. Spins on. Hey, that's not nice. Yeah. All right, so far 1 legit answer has come in. I'll keep going. I haven't agreed with anybody yet, though. I have answers. You can always change your answer. If you're doing it privately, you can always change it. So, so far I've had no correct answers in yet. Radians per second. Now, think about this. Radians per second. If it was, okay, here's a couple things to keep in mind. How many radians in 1 complete revolution? Okay, Andrew sent something in, and that looks better. I don't know if he's right, but it looks better. It's going to be a small number, and Andrew would agree with that. It's going to be a small number. Okay. And anything okay, if the Earth spun around once every second, we'd all be thrown off, but that would be 2 pi radians per second, right? If the Earth went around once a second, but it doesn't, right? It goes around once every 24 hours. But I want it in radians per second. So keep thinking, keep thinking. Andrew so far has got, it seems pretty correct. I haven't checked it. We'll check it in a second. But let's get some more of those in there. Give you another minute. You can guess as many times as you want. You know, there's no penalty. Okay. Natalie has something in. Not the same as Andrew's. What I'm saying is think small, because if it takes the Earth 24 hours to go all the way, think about that little puppy. That puppy ran around in a circle. He was going at pi radians a second. But the Earth, no way, is spinning that fast. So, see what I'm saying? So if you think back to the puppy, that's your basis. That's pi radians a second. Earth kind of spins pretty slow. Okay, so I'm standing up. I'm in a flying saucer. I'm watching the Earth go round and around. I pick a point. Say I pick. I start watching Toronto, Canada. Okay, so I start watching Toronto, Canada, and the question is, how long will it take Toronto to come back around and be at the same place? Okay, Toronto. I'm watching it spin. And if it did it in like 2 pi, if it went all the way around in 1 second, I'm like, oh my gosh, that planet is humming. So it's 2 pi radians in what? How long does it go all the way around? 24 hours last time I checked. Right? But all I got to do is get this in terms of radians per second, right? So 2 pi radians in 24 hours, just simply go, okay, a little quick unit analysis, an hour over 3,600 seconds. Now I'll allow that. That's a combo, which I don't really like, but we do it so often. So that should do it. And is Ramsey correct? Is Andrew correct? Let's take a look. 2, which is 6.28 divided by parentheses 24 times 3,600. Close parentheses. I get 7.27 times 10 to the first, second, third, fourth, fifth, 10 to the negative fifth radians per second. That's the speed of the Earth, if I'm right. So it looks like I'm going to give it to Jacob. I'm going to give Jacob the 2 points. I'm going to give Roman the 2 points. I'm going to give Ramsey. He redid it, which is perfectly legal. You can go through and do it. Ramsey, he said, okay, he's right. He corrected it. And he had it as negative at first, which meant the Earth was rotating the other way around, which means the sun would rise in California and set in New York City. He said, no, it should be positive. Okay, so I'm going to give it to Jacob, Roman, and Ramsey. 2 points each. Good job. Okay, good. Those points may start to add up after a while. Let's see what happened in first hour. That's how we did it in first hour. We did it in inverse hours in first hour. Oh, but we got into this discussion on MKS. And write down MKS in your notes. And someone last hour said, boy, where do I write this down? Just a piece of paper. If you have a notebook, if you're a class scribe, you should be kind of putting together something nice and neat eventually. But put in your, just in a piece of paper, put 928 and then just all your scribbles. And then you'll staple all that. Logan's asked the question, do we use 2 pi because of circumference? Yes. Well, no. Actually, it's a great question, Logan. That probably shouldn't have been private. Should have just made that in public. But Logan asked the question, do we use 2 pi because of the circumference? We use 2 pi because of the rotation. We didn't mention a word about, that's a great, I'll give you a point on that one because that brings up something. We didn't mention a word. We talked about Toronto. But is it also, let's say we used Oklahoma City. Would we still get the same value? Okay. Emerson has to go, but I will record this, but it is being recorded, I think, I hope. But it'll be posted tomorrow at around noonish. Okay. So if I had said Oklahoma City, what if it was OKC? How would I have to change my answer if it was OKC? That's how fast that's Toronto's omega from the North Pole. What's Oklahoma City's omega from the North Pole? I'm going to give you two more Zoom points for this one. If you can answer it, but this time answer publicly. What would be the answer for Oklahoma City? Going once. Dare to be wrong. Going twice. Let me give you a hint. There's no calculator required. Going 3 times. Oh, the tension. I'm starting to sweat. Come on, come on, come on, let's go. Avery, get in there. Brennan, you were hot earlier. Timothy. Keep wanting to say Timothy, man. I'm sorry. I've watched that video too many times. Olivia, you've said nothing. Come on now. Jump in there. You can always be wrong. Daniel's very quiet today. Okay. Oklahoma City, I'm running out of time here. Oklahoma City and Toronto have the same omega. Because, watch. It's like spokes on a wheel or this little frisbee. All of this stuff, all these little points here I have, all of these are moving at the same omega, right? If they're like they all go one complete revolution in, say, whatever, 5 seconds. That's all the same. The actual speed changes because you know, that's how fast they're moving through space. All right, think about that one. Well, let's do this ant. We got an ant crawling on a basketball. And we have a radius. And the question is, what's the velocity that gives the velocity of the ant in 2 inches per second? So we got a basketball here, and we got an ant crawling along the basketball, okay? And the ant's moving at about 2 inches a second, fairly quickly, 2 inches a second. And we know the radius of the basketball, and we're supposed to figure out what is the angular speed. So we're supposed to figure out omega. What is omega? All right, now this is going to require a new equation. Let's write down all the equations we know that we can use so far. We have V equals delta S over T. That's a red equation. A black equation we have now is omega equals delta theta over T. That's the analogous. We have also, what the heck is delta theta? Black. We have delta theta equals delta S over R. And what else do we have? That's probably enough. Now what I got to do is I've got to mesh these three equations into one equation. I got to make these three, in other words, I want an equation where, let's go blue, neutral color. I got an equation here where V equals something in terms of omega, okay? So I want to get V on one side, I want to get omega on the other. And so what do? I have, these are my givens. I've got to manipulate these, so I end up with V equals, and by the way, I hate to say it, we're going all the way to 1140, I'm sorry. V equals something in terms of omega. I want this to be a bridge equation between linear world and circular world. So let's take a look. If I start off with, there's a little derivation here. If I start off with V equals delta S over T, but then I go in and I say, okay, wait a minute. I can rewrite this because how about I do it this way? What do I do? Oh, okay, here we go. Look, delta S up here, I can rewrite this. Delta S is equal to omega R, right? If I rewrite that. So now I come down and I substitute omega R for that. That's legal, right? Then I have V then equals omega. Oh, okay, wrong. Sorry, I knew that was someone right there. Delta S equals delta theta. Golly, I'll have to delete that. delta theta times R. Okay, delta theta times R. I'm getting nervous now. I'm running low on time. It makes me nervous. All right, so this is, fix that, sorry. My bad. So we have delta theta times R over T, okay? But then I know that delta theta over T, if I look up here, this kind of stuff that physicists do. They're always manipulating equations and substituting stuff in. So I know delta theta over T is omega, so I can say this equation, a new equation for us. V equals R omega, because this delta theta over T, this was omega. And so I have this equation, and this is called a bridge. And bridge equations link up different worlds. This bridge equation links linear world. This is linear world. If I could spell linear world to circular world. Okay, so it's called a bridge equation. So the point is we can use this equation to quickly solve this. I know in this problem, I know that R equals 4.5. There's my R. There is my velocity V. And I'm trying to find out the angular speed. I'm trying to find omega, right? So once I have the bridge equation, it's pretty easy. I just say, okay, V omega equals V over R. And so, easy enough, omega equals V, which is 2 inches per second, over R, which is 4.5 inches. Okay? And we punch it in, we get inverse seconds, right? Inches cancel. So over here, then we punch that in, and we get whatever, 2, why did I make my numbers so stupid? Keep them simple. 2 divided by 4.5. 0.444. All right, so equals 0.44 inverse seconds. That's how fast that ant is moving. A lot faster than the Earth. Okay. Now, I want you to, I'm violating a rule, I'm rushing physics, but I want you to try and solve number 11. It's the last thing we'll do. We got 8 minutes. Let's solve number 11. And I'll shut up and let you just work it for a second. And I gave you information. I gave you probably too much information here. You don't need all this, but we'll go ahead and circle and label. That's my delta S. So now we're talking about from Beijing to Shanghai. Cannot find, no, Beijing used to be called something else, right? No, there it is. Okay, so Beijing is up here and Shanghai is down here. So that's 820 miles. So it looks, we can look at the Earth and go, okay, that's curved. But like, it's why these flat earthers, I mean, they're morons, but flat earthers think that the Earth's flat because in their egocentric, idiotic version, they look outside and they go, I don't see no curve. So obviously it can't be curved. So, but it looks flat. I mean, you drive from Oklahoma City to Norman, it seems like you're going flat, but really it's a curve. It's just a very, it gently drops off. because the radius is so big. I mean, astronauts say on the moon, when the astronauts stand on the moon, they feel really funny because they can see it curve away from them. But the Earth is big enough where you don't really see the horizon. But the astronauts say on the moon, the horizon's like right over there. Like, oh my gosh, I'm gonna fall over. But so it is a curve. It's actually what we're seeing is we're seeing that train. It's a slice of the Earth. We're seeing that train go from Beijing to Shanghai at 820. Delta S is 820 miles. But the question is, what's its omega? How fast is it moving in terms of omega? The radius of the Earth is, it says there, 6.37 times 10 to the 6th meters. We know a speed here is 300 V is 300 miles an hour. And give us the conversion there. So look at it here, I got another prop. So the Earth, although 820 miles seems like a long ways, because if we're taking a pizza slice down to the center of the Earth, we're taking that pizza slice. And so this is really omega, theta wise, that's not that much. Even though it's 820 miles, theta, it's what? I don't know. Maybe pi over 10. Okay. So yeah. All right. So 820 miles. So we're supposed to come up with what is omega. And we know that omega equals V over R. In this case, it's a particular R, so we say radius of the Earth. If it's a particular R, you make it a capital R. And so we got it. We have 300 miles an hour over 6.37 times 10 to the 6th meters. Now we got a problem because the units don't match up. Remember that omega is supposed to have units of inverse seconds. So I want omega, let's say I want omega in terms of inverse seconds. Question mark, inverse seconds. So I got to do some manipulation here. I told you how many feet are in a mile. And then there is 0.305 meters in a foot. So you guessed it, we need a little unit analysis. I'm kind of rushing a little bit because I'm down to 3 minutes. So my V is 300 miles per hour. My 1 over R is 6.37 times 10 to the 6th meters under 1. And then I'm trying to end up over here at inverse seconds equals, son of a, all right, here we go. Equals, get out of here, world. Equals, I get nervous, see? When I'm not nervous, I start to stutter. That's an old rap song, I think. Equals inverse seconds. And I get nervous, I start to stutter. What is that song? Anyway. So 1 over 6. So now what I got to do, I got to end up in, I'm trying to get into inverse seconds. So I'll get the low hanging fruit. We got an hour over 3,600 seconds. We got my green kill pin, kill the hours. I want to save the seconds. Now I got miles and meters to take care of. Given that it's 5,280 feet in a mile. Green kill pin kills the miles. Now I got meters and feet, and 0.305 meters in 1 foot Green kill pin, kill, 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 kill. Left with whatever. I mean, you punch it in then. So you end up with 300 times 5280 times 0.305 and divide that by 6.37 times 10 to the 6th times 3600. And that all ends up being your answer, equals question mark inverse seconds. And that's how fast this train is moving in radians per second. Okay, that was a mouthful. I recorded it so you can go back and watch it in slow motion. I'm nervous to start to stutter. That is an old Will Smith song, way back. All right, so your homework is number 12. Number 12. Homework is two things. Wait, I think it's just number 12. That's it. Finish everything on 1.6, including number 12. And you'll turn it in Wednesday night. Okay, I think that's it. There's no take-home test out there. Get late stuff in. Okay, so, and Olivia is asking for a question, a private question. So I guess we'll cut you guys off. You guys go ahead and go to lunch, whatever you got to do now. And you can drop off now. I'll answer. Let me stop sharing the screen. Okay, so go ahead and ask your question. You can either ask it or ask it live if you want. So she's asking a question about the submission of the take-home test. Now, Olivia, are you having trouble with that?
So I tried to submit it yesterday because on my computer there wasn't a spot for me to like upload a picture. Like there was a button that said submit, but there wasn't a place to upload. So I did it on my phone.
Yeah, so that's what you're supposed to take a picture.
Yeah, and then I just.
You have an iPhone?
Yeah.
Okay, see iPhones, you know when they take a picture, they keep a little movement before and after, which is ridiculous. It drives me crazy. That's a HIVAC, something like that, and Canvas won't take that. So you have to, when you go on your iPhone, you have to, when you take a picture and you're going to submit that, you have to save it as like a JPEG.
It was a JPG or something.
JPG
so
should work.
It last night I tried to submit it and it apparently didn't submit. So I just resubmitted it this morning.
Did it submit this morning?
Yeah, it went through.
Well, what was the problem last night then?
I don't know. I thought it submitted, but then I checked this morning and it said it failed to go through.
Could be some kind of Wi-Fi thing or something.
Yeah, probably.
Okay, I'll tell you what I'll do. I'm just going to blank it. Now, the way it's set up on Canvas to give you a 5% penalty for today, but you're the second person now that said they had trouble. So I'm going to go ahead and either I'll change it on Canvas so that it's due today, okay, due at midnight tonight, and then that should alleviate the late penalty.
Okay, thank you.
Now wait. If you find out that it didn't, then I'm going to have to go in and hand fix it.
Okay.
So let me know, Olivia. Just send me an email through Canvas. Say, hey, didn't fix it.
Okay.
I'm going to do that as soon as we get off the air here. I'm going to do that right now. And then if in a couple hours you go back and it still is giving you a late penalty, then let me know.
Okay.
Okay.
Thank you.
All right. Anybody else before we go?
I do.
Yeah.
So it like randomly kicked me out of the Zoom right in the middle of question 10. So I saw it said like bridge, but I missed what you said. So could you like explain that real quick? Cause I wasn't there. It kicked me off.
Yeah. And there will be, I'll give you a short answer, but there'll be I'll put the recording up. It'll be up tomorrow at noon, but the bridge, when it says bridge, it means a bridge between linear and circular world.
Okay.
So like every equation, like F equals MA in linear world is in circular world, that's torque equals I alpha. But in other words, it's an identical equation. So for this, we say that velocity equals delta S over T in linear world, Well, in circular world, it's omega equals delta theta over T. And then there's bridges between the two worlds. And we showed the derivation of that says that I have, well, I'm going to share the screen again, but it says that V equals omega R. The bridge equation is velocity in linear world is equal to omega times radius. So that's a bridge equation. And you can use that, you use that equation to solve both the ant on the basketball and the train in China. Both those can be solved with that one equation. Yeah, V equals omega R. Just, you can just almost plug it in with the ant one, but then with the China one, you can plug it in, except you got to do a little manipulation of the units.
Okay.
But I will post, I'll post that key tomorrow at noon.
Wait, is
I'll post the screen. I'll post the video.
Okay. Okay. Thank you. I appreciate
All right. You bet. All right. Bye-bye.
it. Thank you.
Bye, everybody.